Hello friends, welcome to the mechanical properties under the edge of the polymer testing. And in this particular segment, we are going to discuss about the impact strength. Now we have covered the different mechanical properties in the previous lectures like shear properties, lap or sandwich test, we discussed about the standard test methods. Apart from this, we discussed about the flexural properties like flexural stress strain test, 3-point loading, 4-point loading, cantilever test, standards. In this particular segment, we are going to discuss about the impact strength. Under this, we will discuss about the factors affecting the impact strength. We will discuss about some specific tests, pendulum methods, and drop methods. Now, impact strength, this play a very vital role in the all kind of property determination or characterization of polymer samples. Now, the total toughness of a plastic material is directly correlated with its impact characteristics. Now, most individuals may easily understand the concept of toughness, and a generally accepted definition is the amount of effort required to shatter a test piece or object. One of the benefits of the impact test is that it provides a quick estimate of the real energy needed to break the test component. Both the acts of starting at a crack and allowing it to spread through the material require energy. Now, crack initiation energy is the energy required to start a particular crack, and the crack will continue to spread if the system's available energy exceeds and the crack initiation energy, and the full failure will result if the system's energy is sufficient to also exceed to the crack propagation energy. Thus, the impact energy that has been measured is a result of both crack initiation and a crack propagation. And there are 4 common types of failure that are experienced under impact. The outcome of the impact test may produce different failure types. The outcomes of the test showing the subsequent failures, a brittle fracture occurs when a portion widely fractures without giving way, and it frequently has a sharp or glassy edge. Under the impact situation, general purpose polystyrene frequently demonstrates this particular type of a failure. Ductile failure, this occurs when there is a clear material yielding, which is frequently indicated by the stress whitening in addition to cracking. So, generally speaking, the polyolefins are thought of as a ductile material. The yielding occurs when a portion has clear irreversible deformation and stress bleaching but does not crack. When a part exhibits some cracking and yielding but keeps its shape and integrity, that is considered to be the mild cracking. There are various factors affecting the impact strength. One is the rate of loading. Now, given that a plastic material, they are the viscoelastic, the speed at which the test piece or component is struck has a substantial impact on how the polymer respond to impact loading. Although even rubbery material will show brittle failure at high enough impact rates, comparatively stiff material that can nevertheless have considered impact strength at low impact rates. Now, this appears to be a critical velocity over which all the polymer material become glassy and brittle. Now, it is risky to base a material choice on standard impact test like Charpy or falling weight when a product will see impact speed of say 50 meter per second. Now, because these impact velocities are an order of magnitude lower, and a material that behaves ductility at these speeds may become brittle at the application speed. So, after utilizing these tests to screen perspective, the candidate material for the uses a more specialized and likely ad hoc test may be required, and this may be involving shooting a projectile at the material. Another thing is that in question, that is temperature. The influence of temperature on plastic is far more pronounced than it is on material like metals and ceramics due to the viscoelastic nature of polymers. The temperature reduction tends to accelerate the development of brittle failure. Therefore, it is crucial to consider the temperature range that the item may encounter while in use and to conduct the impact testing over the temperature range as practically as possible. One point should be noted that rising temperature has the reverse impact on speed. Therefore, the change from ductile to brittle behavior occurs at a locus of temperature or speed values rather than at a single temperature. Notch sensitivity. The impact strength of a material can be significantly reduced by a sharp corner in the manufactured item or notch in a test specimen. This is due to the fact that a notch produces a localized area of concentrated stress where the actual stress may be significantly greater than the bulk load placed on the test piece or object as a whole. Though the notch sensitivity varies depending on the type of plastic being evaluated, all polymers are notch sensitive. The impact behavior of the material is influenced by both notch depth and notch radius. Uh, since there will be less stress concentration and a bigger radius of curvature at the base of the notch, the material in issue will typically have a higher impact energy. Now, it is clear from that notches, the sharp corners and other elements that concentrate stress should be avoided when designing a plastic item. Let's talk about the failures. A polymer's natural impact qualities can be changed by simply adding a filler of some kind so that the mechanical property may get changed. Now, the polymer impact modifiers can be used as a crack blunting zone or as barrier against the approaching the crack fronts. The creation of ABS by mixing the polybutadiene rubber with styrene acrylonitrile SAN, the plastic is a good illustration for this particular approach. Now, to enhance the impact behavior, plasticizers with a lower molecular weight, they are also being used. When it comes to nylon, raising the moisture level greatly enhance the plastic toughness. Now, if the equilibrium impact strength is to be determined, very dry nylon like nylon 6 and 6,6 must have enough time to absorb air moisture before testing, and this makes them highly fragile. Plasticization has a drawback of causing a loss of stiffness. Now, utilizing fibrous fillers that appear to serve as a stress transfer agent may increase the impact strength. Let's talk about the orientation. Now, since polymer molecules are lengthy, spaghetti-like structure, the flow pattern of the molten polymer during the molding phase have a significant impact on how the molecules are arranged inside an object. Additionally, the molecules have extremely directed properties. For example, like qualities along the main backbone chain differ significantly from those along side chains and across molecules. The impact behavior of the polymer will be significantly influenced by the way the polymer molecules are oriented in a portion, and the impact strength is always greater in the direction of flow. Now, by drawing films and fibers, for instance, the molecular orientation is purposefully imparted, increasing the material's strength and toughness in the stretch direction relative to isotropic material. Though the impact qualities, these can be greatly diminished the right angle to the flow or drawing direction because intermolecular force rather than intermolecular forces are mostly at play. A molded part This impacts characterization at various places or directions. This may differ significantly as a result of directional orientation of the polymer molecule. The impact stresses, they are frequently multi-axial and they have a tendency to discover the mold's weakest direction on their own. The processing conditions also play a very vital role. The processing circumstances can have a significant impact on how a material will react under impact. A material's intrinsic toughness may not be achieved due to improper processing conditions. The inadequate drying of plastics with the propensity of to absorb moisture can significantly reduce the resulting impact strength. The poor processing condition may create voids, for example, that will act as stress concentrators. The high processing temperatures may cause a thermal degradation and therefore reduce the impact strength. A weak weld line might be produced by a poorly designed mold, which would almost likely diminishes the overall impact strength. The impact strength or impact resistance of the test piece extracted from the compression molded plate is typically lower than that of test piece directly injection molded, and the impact strength of test pieces with molded notches are higher than those of test pieces with the machine notches. Now, molecular weight and degree of crystallinity, this also play a very vital role. When all other factors are equal, a decrease in average molecular weight decreases the impact strength and vice versa. However, the effect is rather small above a certain critical molecular weight. The degree of crystallinity is in semi-crystalline polymer like polyolefins. This diminishes the impact resistance and raises the risk of brittle failure. Therefore, the thermal history of the product will affect how an impact event plays out. The identical material will be more durable if it has been quenched from the melt than if it has been allowed to cool slowly. The impact methodology, the impact finding can be greatly changed by the test piece geometry and the way it is stuck. Therefore, a pendulum impact test will yield a different result than a falling weight test. So, by dividing the energy extracted from the pendulum by the cross-sectional area behind the notch, the pendulum tests the normalize the impact energy for a given test piece. It is discovered that the different test piece size, they tend to produce the varied impact data. Now, all of this makes it challenging to directly and quantitatively apply effect data to design estimates. Additionally, it indicates that we must always compare similar items with like items when comparing database for material, or else an erroneous conclusion would have invariably result. There are certain specific tests like pendulum test and falling weight test. There are also two main categories into which the plastic impact testing often falls. The pendulum methods, one is the CHARPY test. The CHARPY test specification can be found in BS EN ISO 1791 and the associated ASTM D6110. In the CHARPY test, the test component is held up as a horizontal beam and is broken by a single pendulum swing with the line of impact falling in the middle of the supports. Now, these test pieces, this may be tested both with and without notches, and they may be oriented either edgewise or flatwise. You can see in this particular figure that this is the edgewise impact side elevation, and this is a plan view of edgewise impact, and this is the side elevation. You see that the flatwise impact, and this is the flatwise impact with the plan view. Now, the test directionally is best understood in reference to the actual dimension of the test item. The center parallel section of the multifunctional test specimen can be used to cut the standard test bar, which has the dimension of 80 into 10 into 4 mm. In the flatwise test, the direction of the pendulum at the impact is in the test piece 4 mm direction, causing bending over the surface of 80 into 10 mm. The edgewise testing, the pendulum swing in the direction of the 10 mm dimension and is bent on the 80 into 4 mm piece. For the majority of the test needs, the edgewise test is now the chosen the geometry type. In the past, the edgewise test was the only used to examine how fiber reinforcement affected impact strength. The flatwise test was the usual norm. Now, it is possible for a laminated test piece to have lamination that are parallel to or maybe normal to direction of blow during either flatwise or edgewise testing. Uh, the type A notch, which has a radius of 0.25 mm at the notch base, the favorite one. Additionally, the covered are the extremely sharp 0.1 mm type C notch and a bland 1 mm type B notch. The flatwise test can also be done with or without notches. However, in this case, the notched test contains two notches that are machined across the 4 mm direction and opposite one another, giving the test piece a 6 mm width in between the notches. Now, this edgewise test allows for the uses of all three notches. Like here you see that this is the type A notch and this is the type B and this is the type C, and this the normal edgewise and a normal flatwise, different type of a direction of the blow in each case. Here you see this is the parallel flatwise and this is the parallel edgewise. The standard test piece is adequate for general testing, but when testing sheet material, it is acceptable to test the sheet's entire thickness up to maximum of 10.2 mm. Above this, the sheet should have one surface cut to get the thickness down to 10 mm. Now, if the sheet is strengthened in any way, the reinforcement must be evenly spaced out and a single type. Thin sample, they are inappropriate for this particular test because they may buckle when tested edgewise or bend without breaking when tested flatwise. Alternative geometries with no prescribed specimen sizes are allowed for long fiber reinforced polymers. The determining factor is actually the span of thickness ratio L by H ratio of 20. They are recommended for type 2 test pieces, while 6 is preferable for type 3 test piece. However, when a ratio is of say 8 is authorized when testing thinner sheet material, since the apparatus cannot tolerate such a small ratio. For a flatwise test, the test piece width is either 10 mm or 15 mm for large stitch or irregularly made construction. Let's talk about the ISO standards. The two pendulum length covered by ISO standard result in various impact velocities. The one that is utilized the most has an impact velocity of 2.9 meter per second, and the 5 pendulums, they are specified with a range energy of 0.5, 1, 2, 4 and 5 joule. The larger machine, they has the pendulum with the energies of 7.5, 15, 25 and 50 joule with an impact velocity of 3.8 meter per second. The ASTM standards, the ASTM D6110 test is similar in general but different in specified. The preferred test specimen measurements, they are based on the imperial units, but sadly the present standard condition contains a mistake that causes the figure that is supposed to show the dimension of the test piece to really show at the geometry of the anvil that is used for the micrometer. The ideal test piece is most likely 127 millimeter long and 12.7 millimeter wide and between 12.7 and 3 mm thick. The distance between the support is 95.3 mm as opposed to the 62 mm required by ISO. ISOT test. The ISOT test is conceptually very similar to the Charpey test, with the exception that the test piece is clamped at one end just below the notch or the specimen center. If it is not notched, then it is struck by the pendulum that is located close to the other end. Consequently, it is a cantilever bending test. You can have a look in this particular figure about this cantilever bending test. There are various standards attributed to this. Now, details of the test, they are provided by BS European standard ISO 180 ESTM D256 method A, as well as the procedure C, D and E. Now, the 80 by 10 by 4 mm test piece from the multifunctional test piece is the widely used ISO standard test piece. There are three permissible variations: unnotched 0.25 mm radius notch or 1.0 mm radius notch type B. They all are all notched options. The type C notch for isotope is undefinable, but these meet the same criteria as for Charpy. While laminated plastics can be tested flatwise as well using the same parallel or standard configuration as for Charpy, the test is almost always conducted edgewise. In contrast to the Charpy test, the notched isotope can be tested in conventional method with the notch on the same side as the point of impact, or the reverse way known as the reverse notch test. Now, in case of the reverse notch test, the face that is not notched is in tension and there is no stress concentration, rather the notch is subjected to compressive deformation. The isotope makes this arrangement conceivable since the test piece is struck by the pendulum far from the notch, and the reverse notch has the added benefit of making the test piece otherwise similar. The test uses the pendulums with the energy of 1, 2.7, 5.5, 11 and 22 joule and an impact velocity of 3.5 meter per second. Let's talk about the ASTM standard. The test is conducted using the imperial measurement, and the length of the notch as opposed to the space behind it serves as the preferable indicator of impact resistance. The apparatus complies with the ISO test method specification, which were mostly taken from the ASTM standard, and the standard test methods used on material with the impact resistance more than 27 joule per meter, they are covered by method A. And method C is used to calculate lower numbers in an effort to adjust for the energy needed to toss the test piece. Now, in order to do this, a secondary test must be performed on the broken test piece, and this test requires that the test piece halves be put back together, and the energy value that results from impacting the broken test piece is taken as the energy used to accelerate initially stationary test piece. By doing the test at two different notches, radii of 0.25 mm and 1 mm, method D estimates the notch sensitivity. The reversed notch test is covered by method E, and while this is meant for to simulate an unnotched test piece, the standard caution that it might not produce results that are 100% accurate. Let's talk about the tensile test. The specimen in bed type and specimen in head type are the two fundamental tensile impact test kinds. Now, here we have shown this specimen in bed type. The first of them is covered by method A of ISO 8256 and the second by method B. The standard specifies two pendulum length, one of which results in an impact velocity of 2.8 meter per second and other of 3.7 meter per second. The first is used with the pendulum with the energies of 2 and 4 joules, while the second is used with the pendulums with the energy of 7.5, 15, 25 or 50 joules. Let's talk about the method A. The test component is clamped into the suitable holder, and that is fitted onto the apparatus bed of a method A. The crosshead of the holder can freely move around the bed while the other end is rigidly mounted on the bed. Between them, the test piece creates a bridge, like here. When the pendulum is released, it strikes the crosshead arm at the bottom of its swing. Now the kinetic energy is transferred to the test piece, which stretches until it ruptures, and the amount of energy received is calculated from the pendulum's height of the swing. The crosshead throw, however, also uses some energy, therefore a compensation must be made for this. For a specific pendulum and a crosshead, the correction can be calculated using this particular equation, like EQ is equal to E max mu 3 plus mu over 2 into 1 plus mu, where mu is equal to 1 over 4 MCR over E max GT over pi square into 1 minus cos alpha, where this EQ, this is the energy correction due to the plastic deformation and kinetic energy of the crosshead. E max is the maximum impact energy of the pendulum. This MCR is the mass of crosshead. G is the acceleration due to the gravity. Obviously, when it is striking, you need to have that G into account. T is the period of the pendulum, and alpha is the angle between the position of the maximum and minimum height of the pendulum. Now, the desired energy to break the test piece is then simply the difference between the aforesaid corrective energy and the uncorrected energy determined by the maximum swing of the pendulum upon impact. Now, this particular figure shows the several types of the test pieces that are used in the pendulum impact test, like type 1, type 2, type 3, type 4 and type 5. You see the geometry. Let's talk about the method B. For method B, the pendulum is released from the higher position while the test item is clamped into the compound head. The tail of the pendulum strikes a stiff support on the apparatus frame as it approaches its lowest point in its swing and is stopped. The test piece extends and ruptures as the front of the pendulum continues to swing. For method A, the adjustments must be made to energy read from the pendulum swing in order to account for the energy from the crosshead bounce. Now, because the two parts of the pendulum, they are moving in a different direction right away after the contact, in this instance, the adjustment is applied to the reading from the pendulum. Though through the use of the unique calibration process that is described in the standard, the correction for the specific device is ascertained, and the impact of the molecular weight on impact and stress strength properties has been studied using the tensile. Drop method, the falling dart method, because there are only two possible outcomes for each drop in the classic falling dart method. Either the test piece fails in accordance with some predetermined criteria, or it passes. A huge number of test specimens are needed. Now, it is impossible to determine by what percentage it succeed or fail. Therefore, the data must be statistically analyzed in order to determine the average energy, mass or height that leads to failure. The force during the impact can be directly measured and quantifiable. The result can be achieved for each test piece examined using the newer technology, since piezoelectric or resistive transducers are incorporated into DART. The BSEN 66031, the general test of plastic is described. A dart with a 20 mm diameter striker is released from the chosen height of 1 meter, while supporting test pieces are preferably 60 mm square or round and 2 mm thick. Although the standard notes that the different results are expected to result from these two procedures, the test piece may be clamped or unclamped on the support, and it is authorized to employ a striker with a 10 mm diameter. The two methods that are chosen are the statistical or probit method and staircase method. Let us talk about the staircase method. Now, depending on whether the test item that was previously tested passed or failed, the mass of the dart is changed in predetermined increments. If it is succeeded, the mass is increased to increase the likelihood that it will fall again, and if it failed, the mass is dropped to reduce the likelihood that it will fail again. Now, to choose an appropriate beginning, mass and increment, at least 20 test pieces must be produced along with an additional 10 utilized as a preliminary specimen. Throughout a particular test run, the increment by which the mass is modified must remain constant. Let's talk about the statistical or probit method. A minimum of 40 test items are needed, although in practice 60 or more are frequently necessary. Here 10 test parts are tested under the specific circumstances and the failure rate is recorded. After making the further adjustment to the mass, another 10 tests are conducted and so on until at least 3 results are achieved with the percentage failures greater than 0 and less than 100%, with at least one result greater than 50% and at least one result less than 50%. Now, in this test, energy can be applied in non-uniform increments, making it similar or simple to assure the equitable distribution of outcome while the test is running. Although it is not the recommended method for conducting the test because the impact velocity changes along with the impact energy. It is permissible to adjust the height rather than the mass of both tests. For testing plastic pipes, the variable falling height method is described in BSEN 1411, which is also dual number as BS 2782 method 1108B. Now, in order to calculate the mean impact strength and standard deviation using the staircase method or statistical method, the percentage of passes or failure is plotted against the impact parameter, that is energy, mass or height depending on the requirement, and the best fit straight line is found. The parameter with a 50% failure chance is called the mean value, and the standard deviation is the difference between the parameter and the 50% and 16% or 84% failure probabilities. So, dear friends, in this particular segment, we have discussed about the mechanical properties and the testing protocol. And we discussed about the IJOT test and the Charpey test and drop test for the characterization of the polymeric samples. And for your convenience, we have enlisted a couple of references which you can utilize as per the requirement. Thank you very much.